present more technological or manufacturing, material manufacturing lecture about ODS alloys, which we aim to very high temperatures, up to 1,300 degrees C. And I'm from the Institute of Physics of Materials of the Czech Republic in Brno. So this is the outline of my talk. And the motivation is basically that we think that the potential of ODS alloys is still not fully used. They are investigated at lower temperatures, let's say up to 800 degrees. And since the yttrium particles are very stable particles and they don't coarsen at high temperatures over 1000 degrees, we aim to improve the current design of the ODS steels. So currently the use of yttrium oxide is about 0.5% of volumic fraction in the materials. There are some commercially produced or non-commercially produced materials, and they have very good grip strength due to interaction between the dislocations and oxides. There is some disadvantages, which is very low creep fracture strain due to the mechanism of the fracture. I will talk about it a little bit more later. And we are exploring the iron, aluminum, chromium, yttrium oxide based system with the oxygen content up to 1.5 weight%, and it has about 5 volumic percent of the yttrium oxide. The aim of this study is mainly to look at the influence of the additional metallic yttrium, which is added to the powder to capture the remaining oxygen, and the rolling temperature on the influence of the rolling temperature on the strength and grip properties. We call this alloy Fe alloy, which is easy name. And if you look at the currently used high temperature materials, they are basically nickel based iron. There is not too many iron alloys except these ODS alloys, which is this PN2000 or Incolloy MA956. And our aim is to move to, this is the Larson-Miller parameters, which is used in creep. You can see that it's depending on temperature in Kelvin and creep time in fracture times in hours. And our aim is to move to higher Larson-Miller parameters and higher stress. So this is our our results from two kinds of processing, rotary swedging and rolling. So with the rolling we can get about similar values as this commercial alloy. There have been done many trials in our group with chromium, molybdenum, vanadium, titanium, niobium as small additions in about a few percent, 1% or 2%. We also experimented with aluminum, yttrium and lanthan oxides to optimize the chemical composition. And what we found at the temperatures at about 1100 to 1300 degrees, the best composition is this one: 10% of aluminum, 4% of chromium, and 4% in yttrium oxide. So the basic formula for the preparation is this: basically iron powder, alumina powder, small chromium granules. Then there is a very fine yttrium oxide powder, 3%, and 1% of yttrium granules. which are compensating the remaining oxygen which is coming from the powder surfaces, and this is the input for our material. Then the material is milled in the ball mill. The balls collide, the particles are forged into the balls and form larger protrusions on their surface, then they break off as a large particle, and the process is going on and on. The large particles are broken then, and these processes 1 and 2 are continuously repeated. This is how the powder looks like after compacting. So you can see large particles and very small particles. And then the powder needs to get consolidated, so it's hot consolidated by forming as a rolling or pressing or rotary swedging or forging. We are basically using rolling and rotary swedging as two main principles for our materials. And it's in the can, metallic can, steel can, basically. And after stripping, the compact material is used with very ultra-fine grain microstructure, which has typical grain size of 100 nanometers, and the nanodispersion of yttrium oxide, which has average size 5 nanometers. The material is very brittle and practically unusable. Here you can see the microstructure after rolling, so very small grain structure, microstructure, sorry. And here you can see on the transmission electron microscopy the yttrium oxide particles. So then the third step of the processing is the secondary recrystallization. So we anneal it at 1200 degrees. Several grains grow rapidly at the expense of the ultrafine grains, and the ODS completely or sometimes partially recrystallize. I will show you some results. Where is the partial recrystallization? The ODS, it's not easy to recrystallize it completely, but there are ways. The ODS alloy then becomes relatively ductile and easy to machine as practically normal steel at room temperature, and it has an excellent creep and oxidation resistance at these very high temperatures. So these are the microstructures after rolling. Some early experiments about 4 years ago, and this is the dispersion of the yttrium oxide particles. We looked at the oxidation of our colleagues, looked at the oxidation, so this is from their study. So you can see they compared Cantal and our alloy at 1400, 1300 and 1200 degrees. Cantal alloy is a little bit, seems to be a little bit oxidation more resistant because it's gaining less weight. Or the thickness, basically the thickness of the layer. Here is the thickness of the layer, here is hours of the exposure at these temperatures. And when you look at the microstructure or the surface layer study, so there is very thin layer of alumina oxide formed here. It's getting thicker at higher temperatures, but compared to it, Cantal has some growth which is going through the thickness quite suddenly, and this is not very good sign. So the thickness of the layer is maybe a little bit smaller or similar, but these are not unwanted effects. And now we can look at the mechanical properties. We basically tested at a very slow tensile test at 10 to minus 6 per second strain rate. And when we put the material to the creep test at about 60 to 70% of this measured value, it practically doesn't creep. It will be several thousand of hours up to the creep rupture, because the stress exponent is relatively high in orders of 10 to 40. It depends on the temperature and also on the stress. And the grain boundaries are basically limited cohesive, making the limited cohesive strength, which is the weakest link in this alloy. And there is typically intergranular fracture. It can be avoided by some microstructure, which can be produced by rotary swedging. So we compared, this is one of the older alloys. It doesn't have chromium, it has one titanium in it, weight percent. So when we compare, so the hot rotary swedging is specimens 2, which is this. This is the Ma956 alloy, and this is the rolled alloy. So you can see there is a big difference. This is time to fracture, time to rupture, and this is minimum creep rate. So we can see there is two orders of a magnitude decrease in the creep rate when we have the microstructure with some pattern. Basically, it can be it looks similar to directionally solidified casting, and there can be some comparison of one of the top super nickel-based super alloys. You can see they are very strong up to, let's say, 800 degrees, then they start to drop. So this is MAR M246, polycrystalline alloy, nickel-based. And you can see at the temperatures where we start to be using these materials, which is 1100 degrees, it's still stronger. This is tensile strength at 10 to minus 3. But when we go to 10 to minus 6, it's different story, and for creep is also different story. So this was one of the trials of hot rotary swedging, so you can see it's a little bit better than our material, and this is the commercial, the blue line is the commercial alloy, so we are a little bit better than it. So if you compare the creep curves, we have 3 curves at 1100 degrees C, here for MAR super alloy at 60 megapascals. This is our alloy at 70 megapascal. This is CMS X4 at 100 megapascal, which is single crystalline, single crystal super alloy, and this is at the lower temperature, 750 degrees, but very high stress. So you can see some disadvantage of these nickel-based super alloys is that you get very high primary creep, and then you get secondary creep at about 5 to 12% of strain, which is quite big, already quite big deformation, which makes it practically hardly usable because you don't want your parts to deform. So it seems it can be advantage of these super alloys, of these ODS alloys, sorry. But the disadvantage is sudden rupture. So you can see it's in secondary and there is practically no tertiary creep, but there is sudden rupture. So we still have to work on this, and I think there are ways. We try to study the content of yttrium, metallic yttrium in the powder, add it to the powder, and you can see it was 2 batches, one with 4% chromium, one with 0% chromium. So the yttrium is beneficial to the alloy up to some amount, which is about 1.2%, and then it suddenly drops, and it makes the strength is lower because it doesn't recrystallize. It's only partially recrystallized, but it has very high effect. This yttrium content and also chromium content has effect on the size of the grains after the secondary recrystallization. And larger grains means better creep strength. This is some curves from our tensile, slow rate tensile tests. So you can see this is for rolled materials with chromium, 4% chromium and 0% chromium. And these curves, these low strength curves are the curves where there was not full recrystallization. There remains too many small grains and they behave plastically at high temperature. But it has a big advantage that you can form this material. If you can forge it or roll it quite easily, this ultra-fine grain material, and then after recrystallization you can get very high strength. So this is one of the example of one of the stronger specimens, but you can see it still has a non-recrystallized part, a small part, and this is the fracture. So basically there is fracture through the gray grain, and sometimes there is also intergranular fracture. So this is kind of mixed fracture. We also tried to see what would be the influence of the hot rolling consolidation temperature. So this is the temperature of rolling, the second step or third step of rolling, and this is the Vickers hardness. So you can see we get some maximum at about 960 degrees, but for the ultimate strength, there is quite large window between, let's say, 850 degrees and 900 or 1000 degrees basically. So which is convenient, so it doesn't dramatically depend on the rolling temperature. So this is the ductility. You see it's very low values, about 1.5%, sometimes 2%. So I would conclude in the parentheses is the expected properties, which we didn't fully try yet. So we add 5 to 10 times more oxide content to the ODS alloys than the traditional ones. Additional metallic yttrium can compensate the oxygen in the powder, so it has positive influence at these very high temperatures. And there is basically good creep resistance, good strength, and nearly no primary creep, and very low creep rate can be obtained at selected stresses, which are still usable in the industry, I think. So we will now focus on the formability, so we want to try forging of these alloys and so on. And we can produce bars of about 50 millimeters in diameter and sheets about 100. So these are the grips for our grip machine, which were produced from this alloy, and this is Jarý Svoboda, who is the main leader of the project which we are having for funding. So thank you very much for your attention.
Thank you very much for your presentation. The paper is now open for questions or comments, please. Okay, I have one comment, one question. When you presented the graphics, strain versus time, I noticed that the time was not very long, and
typically accelerated creep test.
Yes, because typically when we are talking about creep, we are talking beyond 1,000 hours, more or less. So probably.
Well, we do accelerated creep test because we are developing material. Once we have a good batch, which can be very promising, we are. In fact, we have a grip machines which had problems with grips. That's why we made grips from this material, our material, because the nickel-based superalloys are not able to do tests at 1300 degrees. And we don't have ceramic grips. It's problematic, the ceramic grips. It fractures often, it's very expensive. So we made these grips, and now we will start really the heavy grip series or heavy grip campaign. Yeah.
Yeah.
So we plan to test up to, let's say, 10,000 hours and so on.
Yes, yes, indeed. Because either the temperature is too high or the stresses are too high or something. But the duration of the test should be longer. I guess. Yeah. Yeah. Any more questions or comments? Okay, thank you very much for your presentation.